And I will go ahead and introduce our first speaker today, who is our very own Karina Kufner. So Corinna's research focuses on the ultra-fast photophysics of biomolecules in early stages of evolution, including RNA, DNA building blocks, and the photophysics of oligonucleotides. Corinna completed both her undergraduate and graduate studies at the Ludwig Maximilians University in Munich before joining the Sasolov group as a postdoc at the CfA. And the title of her talk today is The Effects of UV Light on the Origins of Life. So please go ahead, Corinna, and start sharing your screen.
Thank you, James, for the kind introduction. Can you all see this?
Yes, we can.
Okay, great. All right. So, yes, my name is Corinna Kufner. I'm with Dimitar Sasolov, and today I'm going to talk about the effects of UV irradiation on origins of life scenarios. As you all know, the research field of origins of life is very interdisciplinary, including astrophysicists, physicists, chemists, biologists, geologists, among others. So I personally am a photophysicist, so I will be speaking from this perspective today. And I will also focus on early Earth scenarios, but a lot of what I'm going to say also has implications on exoplanetary systems. So when we think about origins of life scenarios, one of the central questions is how actually simple building blocks have formed more complex molecules, such as RNA, DNA, or proteins. So when we think about how simplistic building blocks have become more complex molecules, there are a lot of different environmental considerations to take into account. And this has been a subject of great discussion. So one of the main points here is that for all of these chemistries, you need a driving force. And it's been discussed that a disequilibrium of various kinds is useful. So for example, temperature gradient or a wet-dry cycle or day-night cycle, or even a pH gradient as a driving force for early chemistry to go on. So when we take these considerations into account, a plausible scenario could be, for example, a shallow lake on the surface of the early Earth, where dry cycling would be possible or where temperature gradients can appear. So whenever we speak about a scenario that is related to the surface of the early Earth, then one major point to take into account is that it's very likely that UV irradiation, ultraviolet light, has reached those molecules. So when we think about chemistry that needs to work in a surface environment of the early Earth, then it's also very likely that those molecules were exposed to UV irradiation. Specifically, if we talk about the early Earth, then the spectral irradiance on the surface of the early Earth differ from today's Earth quite substantially, as shown on the right. This was work by Sarah Rukheimer and Sukrajanjan, with the atmospheric conditions on early Earth differing quite substantially from today's. Specifically, the lack of ozone in the early atmosphere had as a consequence that much deeper UVC and UVB irradiation could penetrate through the atmosphere and actually reach the surface of the early Earth. The implication of this is that the molecules that were present on the surface of the early Earth must have had to cope with strong UVC radiation. And particularly if we think about a scenario like a shallow lake, for example, then UV light can also penetrate into these lakes.
Corinna, can I just interrupt you quickly?
Yeah, sure.
That top right plot there, is that taking into account also the evolution of the sun's output at like UV wavelengths? Or is it just like, is that just taking into account the evolution of the Earth's atmosphere, assuming that the sun's output is constant over time?
So I presume this work was done for early Earth conditions.
Okay, so taking into account the young sun as well.
Yeah, so I'm not sure about all the details. I think in this study specifically, they took into account the solar irradiance and the atmospheric gases, but I'm not sure to what detail exactly. So I think scattering effects and mainly ozone, those two effects were taking into account from an early sun perspective.
Okay, thanks.
But I would need to double check again with the authors to be absolutely sure. Okay, so when we think about chemistry that needs to take place in a wet scenario like a shallow lake, and this is close to the surface of the early Earth, then UV light will also penetrate into those lakes. So when we speak about lakes, the salt composition of those lakes is crucial for the UV penetration depth into those lakes. So if we look at the left plot, this shows UV extinction coefficients of various salts that are plausible on the early Earth. And what we started doing was actually to go to different groups, and we asked them for catalogs. What are, in their opinion, plausible salts to be present in lake scenarios on the early Earth, and started doing a catalog. This plot on the left shows only a few examples of various different salt species that could be present in early lakes. And what we generally found is that ferrous species are pretty dominant. So whenever small concentration of ferrous iron is present in an early lake, that acts as a pretty strong UV shield, whereas salts like chloride or bromide start absorbing in the deep UVC range. So that has less effect than a large concentration of ferrous iron, for example. So the implication of this, if we consider a scenario where UV light penetrates into a lake, is that if we take the surface irradiation and model this for an example of a lake scenario, in this case, a specific concentration of chloride, bromide, and iodide, then we can predict the UV penetration depth into those lakes at various different depths. So the spectrum at 1 meter would be the red curve, then 10 meters, 20, or 50 meters. And what you can see is that the cutoff wavelength shifts to longer wavelength. So the deeper we look into a lake, the less UVC light will be present because it's blocked by its salt constituents. But this has implications on the different kinds of chemistry that can go on in various different heights or different depths of the early lake. And again, this critically depends on the salt constitution. So with this, we're able to model different salt constitutions. We also asked different groups about prebiotic recipes for lake scenarios. And this is work that is basically a catalog for different scenarios. So if we think about this in a lab condition, then typical ways to model a prebiotic sun in the lab would be to use, for example, a xenon lamp, as it's shown on the left. the xenon lamp spectrum is shown in black. So what you can see is that specifically the range between 200 and about 300 nanometers is higher with a xenon lamp than on early Earth, the solar irradiance. But it is possible to attenuate the light here. So this could be, for example, done by adding filters or additional absorbers to smooth the spectrum here, or to actually block the deep UVC range, and then to have a simulator of an early sun. This is work that Paul Rimmer currently is doing in Cambridge, UK Cambridge. So they're trying to model early Earth conditions or prebiotic sun with this kind of a simulator. There is a difference, however, in the intensity. So the early Earth irradiation is by about 2 orders of magnitude weaker than a typical lab xenon lamp. And other ways of doing lab experiments are, for example, taking a UV LED, which would be not as broadband, but about 30 nanometers broad, around 266 nanometers. That is currently the deepest UVC light that is commercially available with LEDs. Power is about 1 milliwatt, so that's about a factor of 1,000 above the prebiotic sun. And then what chemistry labs love to do is to use a ray reactor, which is a circle basically of, I think, mercury lamps that emits a peak at 254 nanometers. And then you would put your samples in here and irradiate that for a couple of hours. So that would be a very strong lamp, which is about 4 to 5 orders of magnitude above the prebiotic sun. But this is mainly used as a proof of concept method to see if chemical processes can actually react or happen on the early Earth. So if it's plausible or not. So currently, these are the methods that are typically used in labs to see if chemical processes are actually likely to have occurred on the early Earth under those conditions. So when we talk about the process of making nucleotides or building blocks of life from very simplistic molecules, this is a very tricky question in terms of efficiencies. So on the left, this plot shows a potential reaction network that starts with cyanide, shown in red on the left, and then takes multiple reaction steps to actually become complex molecules such as RNA building blocks. The main caveat of this is that each reaction step doesn't have an efficiency of 100%. So if you look on the right, a typical example, if you had a cascade of, for example, 7 reaction steps where each of them had an efficiency between 30 and 90%, for example, then we would end up with 2 per mil of the reaction product. So this is called arithmetic demon, which is a huge problem in the efficient production of prebiotic building blocks. If we take feedstock solutions in a large supply, if we just move step by step in the chemical network, then it's really hard to get large quantities of the product molecules. There are ways to circumvent this, for example, by inducing cycles. So if you can induce a loop here where a feedstock molecule is used to produce something else, and by rerunning the cycle, one step can be enhanced by a lot, then this can circumvent this problem. But also UV light plays an important role here. So as marked in the picture on the left, there are some of the steps that require UV light. UV light has an ambivalent role here. On the one hand, it can actually kill some of the reaction pathways, so completely eliminate that it's not possible to get one reaction product because it's not photostable, for example. But on the other hand, it can also enhance some of the products because it can provide the energy, or it can also stabilize complexes. And this is exactly what we're interested in and what we're studying in the Sasolov lab. The setup which we're using for this is a pump probe spectroscopy setup, ultra-fast pump probe spectroscopy, where we're using a sample which is excited by an ultra-short UV pulse. Ultra-short is in the order of femtoseconds. That is about a couple of days compared to the age of the universe, if you compare it to 1 second. So really, really short. Then with this pump pulse, the sample gets excited. So you can imagine this as the molecules start vibrating, or they also, like the electronic structure around the molecules changes. And this change can be tracked with a second pulse because the absorption of the molecules thereby changes. So what we do is we use a second pulse shortly after, and we can actually tune the arrival time between the pump pulse and the probe pulse and get a scan of the decay of this molecule in solution, particularly. So on the right, this is an example. The x-axis shows a time scale where at time 0, both pulses would be arriving at the same time. This is the maximum excitation. So here, this is the electron ejection from pure water. So we're just hitting the water very hard with UV pulses and ejecting electrons into solution. So first, we have a lot of electrons here. And then shortly after, this decays exponentially to go back to its ground state within a couple of microseconds. And with this method, we can actually determine rates. So if we go on then and fit exponential into these decay curves, we can determine the decay constants. So that would mean we can actually go back to this picture and give rates for all those reaction pathways, but in real time. So what we do here is actually we monitor the behavior of the photoexcited molecules in actual real time, and can then say, okay, this pathway here is likely to have occurred, for example, but the other one is not, simply because the molecules are more stable, or because one reaction pathway is enhanced or not. So the main takeaways here are that whenever we look at scenarios that relate to the surface of the early Earth, but it can also be on an exoplanetary system, then it is also critical to include considerations of irradiation that could have been present on the early Earth, for example, irradiation in the deep UVC range, because this light particularly has contributions to the photophysics that are going on and can have effects on the selection in the early evolution and also on the formation of the building blocks. So I think I'm just going to end with that. And thank you all very much, and the organizers for inviting me.
Thanks, Corinna. That was fascinating. Do we have any questions? If so, please raise your hand in the participants window. Okay, Juliana, you go ahead.
Thank you, James. Thank you, Karina. That was a lot of fun. Can you scroll down to the plot where you have the different depths there? Oh, that one. Can you go up? Sorry.
This one?
Yeah, so I may have missed this, but do you assume any concentration for the iron ions here? For the ferrocyanide?
So for the iron, this is something that is a huge point of debate right now with our collaborators, because basically the implications of this work are that if you have only traces of ferrous iron, that this will block the main UV light into the lakes.
I see. Yeah, that was my question, because it sort of seems like from the left, I think that shows these are the ferrous iron, the ferrocyanides are so important, but then here on the right, I was wondering if that would just mean you just get no surface intensity, and that just kind of kills some of the chemistry.
Yeah.
Okay.
No, so the plot on the right doesn't include ferrous iron. This is one basic example. But if you include ferrocyanide, this will absorb a lot faster.
Okay.
So ferrocyanide is very interesting to study for another reason as well, because basically if you irradiate ferrocyanide, that emits solvated electrons. So it gives electrons away to the solution in no time. That is just basically every photon that gets absorbed by the ferrocyanide directly emits an electron into the solution. And if you have solvated electrons in solution, this means that these can potentially, so there are two parts about it. Solvated electrons have a very long lifetime, so that means they stay in solution for quite some time. And then they can actually react with other molecules. So they can do reductive chemistry on other molecules just because they're present. So at this point, ferrocyanide is also discussed for another reason, and basically this is what it's a strong electron donor that can have affected the photochemistry going on.
Awesome, thank you.
Sure.
Do we have any more questions? I have a very simple question, probably. Corinna, if you scroll down where you show your light sources and you have like the relative, that's it, intensity to the early sun, is it simple enough to just correct your rates or, yeah, your measurements, I suppose, for each of these relative intensities just by dividing through by each of these relative numbers to get back to what the condition would be for the early Earth?
Yeah, that's a very good question. So it's it makes a difference for some of the photochemical reactions which wavelength you actually use. So if we look at a reaction network and are just interested in simulating early sun conditions, then a broadband light source is a useful thing, like a xenon lamp, for example. But these narrowband light sources are rather used for specific photophysics. So if we think about reactions, like molecule A reacts to molecule B, that can differ significantly depending on which wavelength we irradiate it with. Either, for example, if you irradiate here at 350 nanometers or at 250, there can be completely different photophysics going on. So whenever we use light sources that are broadband, all these processes will happen at the same time. If we use a narrow band, on the contrary, then we can distinguish what exactly are the mechanisms. So there are pros to both sides. If you use a narrowband light source, this is more useful for studying mechanisms to figure out why is a molecule reacting from A to B. If you, on the contrary, are interested in remodeling conditions that are as likely as possible on the early Earth, then broadband light sources are more realistic. So the one that is shown on the right is mainly used for a proof of concept. By chemists, it's very strong. So compared to early Earth light conditions, it's incredibly strong, but there is more the idea behind it to figure out, does the reaction work at all or not? And then in the next step to go back and actually look more closely and say, okay, is it realistic? And then the point that you just mentioned, James, does it is this included in the rate constants? Yes, it is, because then the rates are much slower on early Earth, and sometimes even it turns out that reactions are just too slow to happen on the early Earth. So I would say from this perspective, both considerations are important, because if you don't do it, you won't find out if a reaction actually works or not. But then on the other hand, it also needs to be realistic on early Earth.
Thanks. Interesting. Okay, so it looks like we have no further questions. So thanks again, Corinna. That was great.
You're welcome. Thank you.
And we'll move on to our second speaker. So please, Suri, go ahead.
All right. So our second speaker is Louise Nielsen. Louise finished her Bachelor of Physics and Master of Science from the Nielsen Institute in Denmark. And then she is currently a PhD candidate finishing up her dissertation at the University of Geneva. Louise has been working on the radial velocity follow-up of transiting exoplanets. And today she's going to tell us about transition between ice and gas giants, explore with TESS and radial velocity measurement. So please take it away.
Got on mute first. There we go. Thank you very much. I'm really happy to see so many people here despite of JWST deadline day. So I'm very honored that you found time for me. And then I also want to say that for me, it's super special that we're finally submitting proposals for James Webb, because I actually started my journey in exoplanet science as an intern at the European Space Agency, working with transmission spectroscopy of exoplanets, or future transmission spectroscopy of exoplanets with James Webb. So today I'm going to talk about my PhD work, or part of my PhD work, and everything I'm going to show today is sort of in prep, but I've removed everything that can kind of give away too many details. So we're going to start out with a very complicated diagram. It's probably my favorite picture to show anyone in astronomy. It's this very nice figure of the planets in our solar system. Just want to check, can people see my cursor? Can you see where I'm pointing? Excellent, super. So in our solar system, we have two gas giants, Jupiter and Saturn. And then we have two ice giants, Neptune and Uranus. And then we have all of these small rocky planets. And I hope you're all familiar with the little blue one here that we live on. So in my work, I've mainly worked with giant planets, and I've worked with the difference between what is a Neptune and what is a Jupiter. So that's really what I mean when I say ice and gas giant planets, is Neptune-like planets and Jupiter-like planets. Of course, I think generally it's very strange to use the word ice giant for a Neptune, let's say, in a 4-day orbit around a hot star, for instance, because they probably don't contain that much ice. But that's what we name them in our solar system. So that's also what we're gonna sort of call them in other solar systems. So I think our solar system is quite interesting in the way that we don't really find any planets in between the size of Jupiter and Saturn. And you can, I think it's very clear when you look at the picture the way it is here, that there's like 3 groups of planets in our solar system, and then of course you can break those groups into subgroups. But you have the giant gas giants, our 2 ice giants, and then all of the rocky planets. And the question we've been trying to ask is what happens in between Jupiter and Neptune. So you have to go and look at some theory of planet formation to really understand that. So the plot here on the left side, I always have a problem with left and right. I should be having it on my screen. The plot here on the left side shows the mass of a planet embryo, or a planet as it's forming, as a function of time. And please notice that the time here on the x-axis is on a logarithmic scale. So in the beginning, everything happens at quite short time scales, we believe, at least. I should say that, yeah, this figure, of course, it's from more like 1960s, 1996, well, not 66, 1996. And of course, a lot of stuff have happened in planet formation theory since then, but the idea of core accretion still persisted in the scientific community, and it's still sort of the go-to flavor of planet formation. But of course, there are other formation theory out there, and I'm gonna talk a little bit about that in the end as well. But the idea is we start out with something along the lines of a core, a planet core that has been created by pebble accretion. So you have a lot of small lumps of material that cluster into a core, and then over quite some time, this core will then grow until it reaches a critical mass, and then it will get this runaway gas accretion phase, which is what you see at the right-hand side of that plot. And the idea is once you get to your rapid gas accretion phase, everything happens really quickly. Yeah. So the idea is, if you follow this line of thinking, is that either you will end up with something that's a core-like thing, or you will get enough mass that you will go through a rapid gas accretion, and then you'll end up as a Jupiter. So you can sort of think of this as being Neptune down here and Jupiter up here. So if we believe in that theory, we should have a completely bimodal distribution of gas planets. So we should have a family of Neptune-sized planets and a family of Jupiter-sized planets, or mass planets. I'm going to use mass and radius a little bit interchangingly in the beginning here, but as we will see later, that's not necessarily the same, I think. So of course, any planet formation theory should be able to create our solar system. So when you look at core accretion theory as it is right here, it's really been designed to explain the solar system. And then of course here comes our 4,000 exoplanets, and we're trying to disrupt that image. So that's sort of what you see on the right hand side. Oh, I forgot to put this plot is from Fulton et al. In 2018. I forgot to put the credit on there, but a fairly known result in the radius gap between super Earths and Neptunes. And then we actually don't have that many giant planets once we start taking into account our observation biases. So we find a lot of Jupiters, and we know of a lot of hot Jupiters, but the only reason why we know so many of them is just because they're so much easier to find than all of these small planets down here. That's the size of Earth and Jupiter. So there are some studies that have looked into the occurrence rate of giant planets and different families of giant planets. And according to Su et al. From 2019, which I think is one of the most recent ones, they say it's about, if you take this bin here, which basically goes from Neptune to Saturn sized, it's around 7% of all planets that fall in between these gaps. And what is interesting, especially, is to compare it with the occurrence of Jupiter-sized planets. So as I said before, if we really think that we have this formation scenario where either you're a Neptune or you're Jupiter, and it's very difficult to create anything in between, we should we should expect to see nothing in between here, and then a bump up at the Jupiters, and maybe a bump down here at the Neptunes. Yeah, sorry, just had to check my own reasoning here. So that's not really what we see, but it's quite interesting to really investigate this parameter range. So that's what we've been trying to do. So I like to try to set it up a little bit cartoonish, but yeah, runaway core accretion will make the difference between a Saturn and a Neptune. And then we say, all right, let's go out and see if we can find some of them. Of course, we're not the first ones to have this idea. There's a lot of other people that have been working in this field before. But back in 2018, before the launch of TESS, we thought we're gonna take a little bit of the cake as well. So the idea is to use radial velocity measurements to measure the mass of exoplanet candidates that fall within this parameter range. And we're very lucky in Geneva that we have our own telescope, with the Swiss Euler telescope, which is 1.2 meters in Chile, and we have a high resolution spectrograph on that called Coralie. And Coralie can do about 3 meters per second accuracy when we're photon limited. So if you work in RVs or in radial velocities, that number will mean something to you. And if you don't, then I'm very sorry. But the idea is that with Coralie, we can really do, giant planets, and we can do heavy Neptunes if your star is really bright, but we can't do Earth-sized planets or anything smaller than that. So for smaller things, usually we have to go to HARPS, which is on the ESO 3.6 meter telescope, and HARPS can do 3 meters per second for bright stars. So we have sort of a factor 3 between these two instruments, but HARPS again is on a much larger telescope, so we can also do stars that are a little bit fainter there. So the idea is to combine these two telescopes to do a survey of anything that's between Neptune and Saturn. So anything that's between 4 and 9 Earth radii. The star has to be bright because otherwise we can't do it on Coralie, but really HARPS is also struggling once we go to anything that's fainter than magnitude 12. It also has to be in the southern hemisphere because that's where our telescopes are, and then we also have a cap on the temperature of the star, which is all about whether or not we can do radial velocity follow-up of these stars. So far, we've used 10 nights of HARPS observations and about the same on Coralie for this specific program. I think in my PhD work, I've coordinated almost 100 Coralie nights of observations where we've mainly done vetting of test targets. So we do a lot of other things in Geneva as well. This is just sort of my corner of our pie. And we actually restarted observations on HARPS yesterday. So I'm really, really excited. We're actually starting to get data again. But it's also been very hectic getting back to observing schedules again after not having done anything for 6 months. It's really good to be back on sky. Yeah, so our idea is actually to do vetting on basically all candidates that fall within this parameter range I've been talking about. But then again, also there's some dependencies on period and stuff like this. We can't really do Neptunes on several hundred periods. So most of them are short period candidates. So as I mentioned before, TESS is our go-to source of exoplanets these days, I think it's safe to say. So I just want to say a little bit about TESS and what it looks like so far. So this is based on the first year of from TESS, and I must admit it's been a while since I updated this plot, but it's fairly reasonable for what it looks like still today for year 1 candidates. The idea with focusing on year 1 candidates from TESS is it's basically just because they're better vetted at this point. So we've had a chance to check if the candidate is due to a nearby eclipsing binary, or maybe it's a low mass eclipsing binary. Could it be some kind of astrophysical thing that looks like a planet but really isn't? So the statistics for year 1 is a little bit more solid than year 3, which is what we're accumulating right at the moment. So this histogram shows planet radius, and then we have number of TOIs. So TOI here stands for TESS object of interest. So this is number of TOIs in each bin. And the red bins are all of the TOIs. So this is including things that were known planets to begin with, or let's also say known false positives from the beginning. It's just everything. Then in sort of yellow, you can see in the bottom here, those are all of the new TESS planets. And this is, I think this is pretty true still. So these were planets that were also known to the follow-up community, but maybe not on the archive back in July, August. So it's really nice to see that we're finding a lot of small planets with TESS, but it's also sort of like spreading out everywhere along the radius bins. And then in green, or this kind of teal, I included all of the planets that TESS have discovered that were known planets beforehand. And I kind of like seeing that because you really see the difference between what we could do before and after TESS. So we have a lot of WASP planets up here, some very large planets around fairly bright stars, but we didn't have that many small planets down here. Some of them are hiding behind the yellow, but it's really not that many. So I think with TESS, we're really now entering a stage where we will know, we're really gonna get to a lot of small planets that will be well characterized as well. Yeah, and then the most important for this plot really are the blue ones. So blue is things that are still planet candidates. candidate. That's what PC stands for here. So we have a lot of small planets again, just because there are a lot of them in our galaxy, but we do have quite a bit of candidates around the giant regime as well. So I've highlighted, I think, yeah, I've highlighted the realm that we are interested in. So really, we've tried from Coralie to just say, take everything that's a PC here, so it's a few hundred candidates, and then try to vet them, check if they're false positive or not, and if they look promising, then we try to go for the mass estimate of them. So the plot here on the right side, sort of our money plot so far, but I'm adding a few more points to it these days. But what you see on the x-axis, where they are, I see the label got cut a little bit, is mass in Earth masses. So you have one Earth mass is of the not on the plot, and then 10 Earth masses here and 100 Earth masses here. So Jupiter is 317, so Jupiter would be lying somewhere up here. But we have a very nice big clump of hot Jupiters, mainly discovered by ground-based surveys. And then on the y-axis, you have the planet radius. So we have, and this is also in Earth radii. So we have 10 up here, which is sort of the size of Jupiter. So I've highlighted the radius range that we are interested in for these ice gas giant transition. And then I've shown some of our new detections, and some of these detections are independent detections with of planets that we've been able to confirm with HARPS and Coralie, but most of these planets we're collaborating with other teams on as well. And I think, for instance, this one down here is TY 824, which was published with Jennifer Burton Semquin from CfA as well. So I would like to hear people's opinion on this. The thing I'm gonna say next, and this is sort of what I'm working for my thesis actually on at the moment, is that we've collected all of these planet candidates that were sort of uniformly spread within this parameter range. You can almost see the distribution over here. It's actually sort of peaking in between, and then it falls off to the sides. But in the end, the planets that we have managed to confirm and get masses from, they tend to either be in the top of this range or in the bottom of this range. And then I have like one really nice target that is still staying in the middle. And the reason is a mix of some of the planets that look really promising, and planet candidates that look really promising here in the middle. We have found out after we refine the stellar parameters, we find out that the radius either go a little bit up or a little bit down, meaning that it will either shift to the top or to the bottom in this in this diagram. And it's really it's frustrating, but I think there might also be some interesting science behind that. So I think it's in the TESS community, we keep saying that TESS is not a statistical mission. This is not Kepler. The idea is to find planets that we can, single systems we can really characterize in depth. But of course, we're gonna try to do statistics on it as well. And I think there might be something interesting behind my personal struggles of finding planets that are between 4 and 9 Earth radii. So at the moment, I'm picking candidates for our last season of HARPS observations. And this season, I'm gonna be really strict, and I'm only gonna pick planets that really fall straight in the middle of this parameter range. And then we're gonna see if we can find some more. Yeah, so that was a sort of a rant from my side. So I just wanted to show some example data. So this is TY 181. So this is the star that's right here smack in the middle. And it appears to be staying there, which is very nice. So here on the left-hand side is the TESS light curve. The data is just really, really beautiful. And then on the other side, we see the radial velocity follow up. And here I have phase folded the radial velocities on the period of the planet. So we have a mix of Coralie and HARPS, and I want to, of course, turn your attention towards that. HARPS, we get much smaller error bars than with Coralie, but there's also a lot of scatter around the best fit model here. So at the moment, we're trying to find out if the scatter could be due to stellar activity, and there's definitely a periodicity in the scatter. So if I'd shown you the residuals here in a time series instead of showing it phase folded, you can definitely see that there's an additional signal in there, but that signal doesn't fit the rotation period of the star. So this might be a multi-planet system. So this is another thing I'm thinking about a lot at the moment, is that we've found out that quite a few of the planets that fall within this parameter range, or really fall inside this parameter range, tend to be in multi-planet systems, or in the systems where you have mean motion resonances with other planets. And that would also be the case for TOI 181 if that is actually a multi-planet system. But it's a little early, and I'm getting more data at the moment to really try to figure out if this is an additional planet or if it's just some other signal we see. I do think it could be really interesting if a lot of these planets end up being in multi-planet systems. That could perhaps explain why their radius is a little bit larger, because you could have tidal inflation. That has also been proposed by other teams for a way to explain these strange planets that are not quite Neptunes and not quite Saturn. So really they're actually just Saturns that have been bloated up due to a tidal interaction with other planets or their host star. Yeah, so I just want to say, yeah, stay tuned for our paper that will come out after I hand in my thesis next week. So at the moment we have 9-ish planets. 3 of those systems might be multi-planet systems, so we're sort of trying to find out if all of these planets are gonna go into the same paper or not. But I think there will be a nice addition to the known TESS planets so far. And we're also finishing our survey of all sub-Saturns or ice to gas giants targets from year 1 of TESS. Oh yeah, well, I figured out how to put in emojis in these spreadsheets. I'm very, very proud. And then in the end, the goal here really is to do a population study. So try to investigate the connection of the properties of these planets with stellar properties, metallicity, mass of the star, but also the environment. So that could be, are these planets, do they tend to be inflated, or do they tend to be in multiple systems, for instance, multiple planet systems? And then in the end, we also have people in Geneva working on refining the internal structure models of these types of planets. So try to see if there's something interesting to be said about that. So there's also already a lot of other work done by other groups in this field. So we're gonna try to do a comparison and see if these transitional planets have different internal structures than what we would expect. So thank you very much.
Thank you. Any comments or questions for Louise? You can use your raise hand feature, or I can try to scroll and look at the camera.
I have a quick question. Louise, when you were describing the plot in the panel just above here on the right-hand side, the planet mass against the radius, and you had your pink bar across here.
This one?
Yeah, you were discussing the lack of planets in the middle of that that shaded region, and you cut out. And I'm not sure if it may be an internet connection my end or your end. I'm not sure, but I was wondering if you could just explain that again, just briefly, please.
Yeah. So if we believe in co-accretion formation theory the way it is right now, like the simple version of it right now, we really shouldn't have any planets in between here. We should have some, but very few. So in our TESS observations, it definitely seems like it's incredibly difficult for us to find anything that falls in between here, which of course is not really a statistical rigorous test of it, but that is hopefully to come. But yeah, I think if we don't find that many planets in between here, it's definitely it's like a step towards saying that there's definitely something about co-accretion, and maybe not confirming it completely, but saying that there are things in it that are definitely true. Which I don't think is that's not a crazy statement to make in 2020. But of course, we're trying to challenge the theory, and trying to kind of stick a screwdriver in the wheel and see what happens.
Now that anything can happen.
Yeah.
I see Jennifer Yi. Do you have questions?
Yeah, so for this mass radius diagram, it looks like at fixed radius, your objects tend to be more massive than objects with masses based on TTVs. I was wondering if that impression was correct, and what kind of selection biases might cause that?
Yeah. So actually on this plot, so all of the stars are our new confirmed planets. And then in the blue and gray, we have all of the known planets. I've put in a mass accuracy cut here just to make the plot a little bit easier for the eyes. But the plots are then color-coded by TTV mass or RV mass. So all of the gray ones are TTVs and all of the blue ones are RVs. And that definitely seems to be some kind of, there could be systematics where maybe some TTV planets the masses could be underestimated, or because the TTV planets are in multi-planet systems that could have an effect on either their radius or their mass, which is, I think, in itself a really interesting question. And I know that there are radial velocity teams around the world that are working on confirming some of these planets out here, for instance, try to measure their masses with radial velocities so we can make a direct comparison. Yeah, but it's true. Yeah, actually, when I look at the plot here myself, I see that my planets tend to maybe be a little bit on the more massive side. If there's that could definitely be a confirmation bias there. That with radial velocities, of course, something that's more dense is easier for us to confirm. But generally, our noise floor with HARPS will allow us to do planets all the way down here in this regime. So that's sort of what makes it nice working on giant planets with nice instruments or state-of-the-art RV instruments, is that we don't have to worry so much about our not being able to confirm low mass planets in this specific case, at least.
Joey?
Hey, Louise. I owe you a
Yeah.
paper draft. That's coming hopefully soon. But my question is, and it's a little bit related to what I work on, is the eccentricity of these systems. Are you seeing, like, what kind of distribution of eccentricities are you seeing for these sub-Jupiter, super Saturn? I'm not sure what to call this regime. Just
Yeah, me neither.
But I'm just wondering, what is the range of the eccentricities, and really what kind of precision you're able to get for the eccentricity measurements?
Yeah, so if refining or making sure that we have good eccentricity, either limits or measurements, is part of the program as well. And so far, I'm trying to remember, I don't think we have any planets at the moment that show significant eccentricity. And most of them we can put an upper limit of something like 0.05.
Wow.
But I think it's definitely interesting to discuss in terms of that could also be a source of inflation. But a lot of our planets are also very low and very short period orbits, so we wouldn't expect to see large eccentricities in there. But I think TOI 181 that I'm showing down here in the bottom could be one of those where it could be interesting to discuss whether or not maybe if you add some eccentricity in here, will some of this additional signal go away.
Thank you.
Okay. Any last question for Louise? If not, I have one. So the radial velocity fit that you are showing right now, I'm wondering, what is the precision of Coralie?
Oh, so I'm trying to remember. So this one is the star is slightly fast rotating, so that's affecting the Coralie measurements. I think here on average, I think these Coralie measurements have like 10 meters per second accuracy, and the HARPS ones have 2 or 3.
And what software are you using for fitting right now?
So I think this is an ExoFast fit. So I think, let me see. I think the fit I'm showing here, I haven't modeled the uncertainties on the RB. So this is more to actually show the data as it is. So normally, when I model these data together, then I will I'll end up inflating the RB uncertainty for HARPS quite significantly to
Yeah, I'm just wondering, because HARPS show much more scattering, why Coralie doesn't really.
I think if we continued getting Coralie data, we would probably see more of this signal in there. So I think it could be a mix of the sampling being a little bit different with Coralie, and then it's kind of hard to say because I have this very large error bar thing in the middle. But it is true. I do get a larger jitter term for HARPS and for Coralie.
Okay. So I don't see any hands anymore. So let's thank our speakers again. And I have a couple of announcements before we go. First, we sent out the spring dates for our Exoplanet Presentation Lounge. So please feel free to start signing up or suggest your colleague. And second, as you know that I left, and so we are looking for a new co-organizer to help James. Again, feel free to contact James if you are interested in organizing this and connect all exoplaneteers together. So otherwise, thank you everyone for coming, and we see each other again in the next 2 weeks. Bye-bye.